Hello everyone, this is Professor Bob. This is what we're going to do today. We're going to cover two very simple equations. We're going to cover a population mean and a sample mean. Now here are really my objectives for this. These two equations you already know. You probably don't know that you know them. Maybe you do know that you know them. But one of the objectives I have for today's session is I want you to get used to looking at different equations and putting them in terms that you already know. So these are two good equations to use because you already know how they work. So I'm going to try to wire your brain a little bit to look at mathematical equations and start to be able to read them. It's very similar for any of you musicians out there. It has to do like with reading music. Like for example, you may know simple songs, nursery rhymes. Sing one of them, row, row, row your boat, or something that you already know that was sung to you when you were a child, or maybe a song that you hum in your head a lot. Now, you already know that song. If I would ask you to sing it or to hum it, I mean, some of us are better singers than others, or me, not a good singer at all, but you would be able to at least get your way through it and hum the song and kind of know it because it's already in your head. But if your music teacher asked you to put it to a treble clef or a bass clef, you might not know how to do that. You might look at it and say, I'm not sure. Or how about this? How about if I put two nursery rhymes and I wrote the music, the treble and the bass for London Bridge is falling down, or row, row, row your boat, or something like that. These are nursery rhymes that I learned when I was a kid. And if I would give that to you on a sheet of music and asked you which one is row, row, row your boat, which one is London Bridge is falling down, or whatever, you might not be able to recognize it because you might say, well, I don't know how to read music. That's exactly how math works. Now, when we look at equations like this, you might look at it and not know what these symbols mean. Or maybe you do, but I'm assuming you don't because that's the level of the class that we're in right now. I'm supposed to be teaching these things to you. So the analogy I draw is I try to get you to read math equations like you would read simple music and be able to kind of draw the connection between what's going on in your head to what you see in front of you. So let's get started. I have two equations here. I have an equation for a population mean and for a sample mean. Now, we may know them as an average. Like, for example, maybe to state the obvious, if I'm looking at how many times I drive to school this week, let's just say I have school 5 times a day. So I measure and record how long it takes me to drive to school every time I do that. So what I would do is to get an average time, I just would take all my observations, right, for the 5 days I drove to school, and I would divide them by the number of times I drove to school, 5 times, and I would get the average time it took me to go to school. Now, in statistics or in math, that's called a mean. Now, there is a slight difference. It's an academic difference between an average and a mean. And I'm not going to go into that. If you like, what you can do is you can, on your own time, spend some time and look at the difference between an average and a mean. I personally think it's kind of an academic point, but technically they're slightly different. But for our purposes, they're kind of one and the same. Although, like I said, for those of you that might be watching this a little bit later, I do know statistically that they can mean different things, but I digress. Let me move on. So anyway, what you see here is you see the formulas here for a mean. You see the formula for a population mean and for a sample mean. And for the sake of argument and for simplicity, you already know how these equations work because I'm assuming you already know how to get an average. Good. Great. So let's move on from there. Let's talk about some of these symbols that you see. Before that, though, let's do some pre-work. Let's talk about a population versus a sample. Now, a population is really all possible observations that could be made for a certain observation. And I'm using my words on purpose. I'm not big on definitions. Come up with your own. Let me explain to you the critical thinking behind that, and then you can draw your own conclusions. Let's just say that I want to figure out the average time. How about this? The average sleep time in minutes for every single person in the city of Chicago. The population for every single person in the city of Chicago, I'm using rough numbers, maybe 2.5 million people or so. Let's make it smaller. How about this? The average sleep time for every student at Triton College. Now, what that population would be is that population would be all possible people that are currently at Triton College. So we would say it would be 8,423 or whatever it may be. Now, as you're probably thinking right now with the numbers I threw out at you, right? I threw out the population of Chicago and I threw out the population of Triton College. Now, those numbers are subjective. I mean, because you might say, well, number one, your number's wrong. There's more or less people that live in the city of Chicago. And then you might want to get a little bit nitty on that. Maybe not nitty is a bad word. You might want to get more specific. That's probably better. More focused. You might say, well, does that include all permanent residents of the city of Chicago? Does that include people that are citizens of Chicago, which means that's their home address and they live in Florida? So they're Chicagoans. So populations are really subjective insofar as the numbers that we can come up with. Now, populations don't always mean people. They can mean other things. Like, for example, we might say, I'm trying to think of something different. How about the number of, this is a good one, the number of snakes that may be venomous? Well, there could be different species of snakes, right, that could bite you and poison you. You might want to define venomous. Like, does venomous mean they kill you or just make you sick? Does it mean that, is a constrictor venomous, meaning that it can squeeze you and hurt you, but if it bites you, it's okay? But anyway, the population doesn't always mean people. It could mean things. It could mean places. It could mean really anything that can be measured. So don't think of a population necessarily as people, although a lot of times it means people. Like, for example, I mentioned about the population of Triton College or the population of the city of Chicago. So it can mean people, it can mean places, it can mean things, but think of a population of all possible observations that are even possible. Okay, that's what a population is. A sample is a subset of that. A sample is really, well, just like I said, it's a subset of a population. Usually, when we do descriptive math, which is what we're doing now, remember there's two types of math. Well, for our purposes, there's descriptive math, which describes things around us, right? And there's predictive math, which what we do is we look at all of our measurements of things that we describe and we make predictions from them. So when we look at population means and sample means, we're looking at descriptive formulas. These describe things. Descriptive statistics, descriptive discrete calculations, descriptive analytics. There's a lot of words for this, but we're using this to describe things. And a sample is a subset of your population. Now, what does that mean? Let's go back to our sleep study for Triton College students. So let's just say that we identify our population. Our population are all full-time, part-time students of Triton College. That includes, right, we got to go and we got to define our population. So since we're making this up and we get to define our population because this is our equation, we can say the population includes the remote learners. It can include people that do the remote learning, that do the in-class teaching or the in-class instruction. So let's just say we come up with our entire population. Now, our sample would be a subset of that. Now, why do we use samples? We use samples because in many times we can't get our whole population. Like, let's go back to our sleep study. Let's just say, for example, the population of Triton College is, and I'm making this number up, it might not match the number I used before, but that's okay, is 10,000. Let's use a round number. So 10,000 is our population of Triton College. Now, if we were trying to get the average number or the average minutes that they slept in a night, it may be impractical or maybe impossible to actually go to every student, each person, 10,000 people, and measure this, right? Think about it. It's mathematically, a population is hard to get to. And it is. I mean, for example, if we were trying to do, how about this, the average number of minutes of sleep for every person in the world, what is that? 7 billion? 8 billion? It's a lot of people, right? Physically, and in many cases, we can't get to everybody. We just can't. That's where our samples are important. And we always hear about this. We hear about, oh, the sample size was too small, or that sample size is not indicative to the whole population. Well, that's what that means. It just means that when we put this into an equation and we put this and we do some math with this, that we really have to get samples of our population. Can we sample our population? We can. Pardon me. Can we get our entire population? Sometimes we can. Let's go to the example that I mentioned about let's think about the average time it takes you or me to go to school every day of the week. The population would be 5 because there's 5 possible observations. Well, there's 7 actually if there's school on Saturday and Sunday. Some of you are raising your hand. Okay, but in that case, we can get to the entire population. The population would be 7 because there's 7 days in a week. Or if I asked you this, how many calories did you eat a day last year? The population would be 365 or 366 if it was a leap year. So sometimes you can get to the entire population. Many times you can't. That's the difference between a sample and a population. Now, let's look at some of these numbers here. Let's look at, you see the term X here. X. What is X? We got X here in the population. We got X here in the sample. X is a single observation. So let's look at different observations here. Let's just say, for example, again, we are going to take a sample of 5 students around us, or 5 students that go to Triton College around us. So we might ask them, how old are you? So we get, and we're going to work with integers at this point. We're not going to work with real numbers. We're going to work with integers. So we get 19, we get 18, we get 22, we get 23, and we get 17. So each of these is an observation, right? It's an observation. Observations, a single observation is denoted by X. Single observations are denoted by X. Let me ask you a question. Are these observations a sample or a population? They're a sample. Remember, a sample is a subset of a population. And we use samples if we can't get to the entire population, or it's not feasible, or sometimes we just don't have time. So in our example here, our sample size is 5 out of a population of 10,000. Why? Well, we needed to get 5 samples immediately. We can't get to all 10,000 students of Triton College. Maybe we can, but in this case we can't. So anyway, so what we have here is we actually have a sample size. It's not a complete population, but don't worry about that too much for now. Worry about the X part. So we have X. And again, X is a single observation. Now, for all of you guys now, what I want you to do is to participate here is I want you to get your calculators out because I'm not going to do this calculation for you. I want you to do it. Now, if you just want to watch, you can do that too. Remember, I'm not going to reach out to you and tap you on the shoulder, but I'm not going to do this math for you. I want you to do it. I'm going to explain to you what to do, but I want you to do it. Now, that's the x. X here and x here. So let's talk about this right here. This is the Greek symbol for sigma. If you're in a fraternity, Delta Sigma Phi, Delta Sigma Kappa, whatever, this is the Greek uppercase for sigma. Sigma in math means sum or sum of, meaning that we want you to add all of these guys together. So on the top of what you see for the population mean and the sample mean, we see and say what we call sigma x. Sigma x says take all of our observations and add them together. Sigma means sum means add. So what I want you to do is I want you to add 19, 18, 22, 23, and 27, and that's going to be, well, for now we'll just work with the sample mean. That will be what is on top of this fraction here, the numerator and the denominator. Okay, so what we do here is we got sigma x. Add them up, put that number there. Now we also have two n's. We have a lowercase n here, and we have an uppercase n. N stands for the number of samples, which is denoted as a lowercase n, or if it's a population, it's an uppercase n, which just means that it denotes that these are still the number of samples, but it's for an entire population. Again, if we were, for example, if we were to get all 10,000 n's or 10,000 x's, right, and sum them, n would just mean that this is the number of samples, and in this case, it's the population. It's all of them. We can't get any more of them than this. In the sample, and lowercase just means it's a sample of a population. But n is n. N is the number of x's that we have. So what would n be in the denominator? N would be 1, 2, 3, 4, 5. Right? N would be 5. So this would be sigma x, which is 19 plus 18 plus 22 plus 23 plus 17. That would go in the numerator over n, which would be x. Looks like an average, doesn't it? It is. It's kind of an average. Don't tell anybody, all right? But remember, statistically and mathematically, averages and means are, for our purposes, they're the same. I know I've said this a few times, but in reality, there's an academic difference between them. We'll just pretend they're the same thing for now, just to keep the peace. Okay, so basically we have x bar. That's the bar here. This is called x bar. X bar is the symbol for the sample mean. So the sample mean is equal to, remember, x bar, say it again. That's a funny word. Sure it is. Say x bar. X bar, did you ever watch Mr. Rogers' Neighborhood? Never mind. All right, x bar is equal to sigma x over n. So all you need to do is do the math now. Now it's just a fraction. So you're going to get a sample mean, which is x bar. And it's off the top of my head, it would be, I don't know, you're doing the math. My brain hurts. I'm still drinking my coffee. It's a simple equation. You do the math. So anyway, that is the symbol. This is the equation for a sample mean, an easy one. They're going to get harder. This is training wheels. This is taking something you already know and putting it into an equation that you may not be familiar with or maybe haven't seen in a while. If you've had high school statistics, you've seen this. But yeah, I don't know. It's just like if I teach this class, I see it every day and I see these things every day. So you may not. All right, so let's go back over to the population mean. Population mean, okay, would be kind of the same thing, except n would be all of your n's, right? It would be not 5, it would be 10,000, right? If we have 10,000 in our population. But look at sigma x is the same. It would be sigma x, and then all the way through 10,000 over n, right? But it's still an average, still is, right? It's sigma x over n. N is a big N because this just means it's going to be our entire population, not little n, which means it's going to be our sample. And we got a different symbol here. Anyone know what the symbol is? It is a lowercase Greek symbol. It's mu, mu, but it's pronounced me. Me, or sometimes I'll say mu or mu too, but it's actually pronounced M-E-E, me. Lowercase me. This is the symbol for your population mean. So this X bar is your sample mean, your sample average. Me is your average for your entire population. That's what these symbols are. To review, X is each individual observation. Sigma is summing, in this case, summing X. N is the number of observations. If it's little, it just means that it's a subset of a population. If it's a big N, it just means it is the population. So N here would be 5, N here would be 10,000. And then we just got the symbol that denotes our mean. So the average, I still say that with trepidation because technically they're different. But again, I'm stuck on this. All right, X bar, sample mean, me, population mean. That is it, folks. So just to sum up, again, my objective is to get, in this session, is to get things that you already know and start to draw the connection between what is already in your brain to how it could be mathematically expressed. We call them equations, right? But yeah, there are mathematical expressions. This is easy peasy, isn't it? This is not hard. One of my other objective is to kind of break your phobia of this, where I don't want you to look at the stuff and go, oh, holy crap, here we go. All this shit again I got to learn. Well, it's a lot of the stuff you're already, I didn't swear, did I? Just ignore that. More stuff I have to learn. More crud I have to learn. I don't want you to just survive math. I want you to rock it. I want you to do more than survive it. I don't want you to get through this stuff and go, oh, good. Phew, I made it through it. I don't got to do it again. I want you to be done with it and say, wow, man, that was really cool. I can do a lot with this stuff. I can really incorporate this kind of knowledge into what I do in my everyday life, because I believe a lot of us at some point forget that math used to be fun. I think in somewhere around second or third grade when we stopped the fun word problems with monkeys and bananas and all these little colorful things and number lines. And right when we got in the fourth grade, when we started doing times tables and we started doing Common Core with the rote math and 8 times 8 is 64. Why? Because I said that's 64. Hurry up, do it quicker, faster, 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 faster. And all of a sudden we're like, I don't want to do this anymore. It's kind of like if we were made to do music classes and then we stopped enjoying them and they kept us playing piano. You're going to do more scales. Here's a minor 7th scale. Here's a minor 7th augmented. What does it mean? It doesn't matter what it means. Just practice, 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 practice. And after a while, we just start curling up in a ball and we just want it all to go away. And math shouldn't be that way. Math is enjoyable. Math doesn't make you smart. You're already smart. You're already smart. But math gives you a way to describe things and everything that you're going to do in life, in your vocation, your profession, whatever it may be. Math is everywhere, and math is something that you've already mastered. You just need to rediscover where that is. So 2 simple equations: population mean, sample mean? Thank you for making it this far, and I bid you all a very well and safe rest of the day. Thank you.